In this video, we will compute the surface integral of a scalar function over a surface which is given parametrically. So here the surface is the upper hemisphere, the unit sphere, and it's not parameterized for us, so we need to parameterize it. So one way to parameterize a sphere is using, of course, spherical coordinates. So we'll use the variables theta and phi, and we'll just use the spherical coordinate equations, but we'll set rho equal to 1 everywhere, since we're on a sphere of radius 1. So this will be sine phi cosine theta, sine phi sine theta, and cosine phi. And in order to compute the integral, we'll need these partial derivative vectors, r phi and r theta. So we take partial derivatives, cosine phi, cosine theta, cosine phi, sine theta, minus sine phi, and theta derivatives minus sine phi sine theta, sine phi cosine theta, and 0. And the reason we compute these is because we really need this cross product of the two, which is a normal vector to the surface. So if we compute this cross product, we get sine squared phi cosine theta, sine squared phi sine theta, and finally for the z coordinate we get cosine phi sine phi. And finally, what we really need, the real reason we did the last 3 lines of computation, is that we need the norm of this. The reason being, when we substitute in the integral, ds will be replaced with this quantity. So if we compute the length of this vector, you'll get square root of sine to the 4th phi cosine squared theta plus sine to the 4th phi sine squared theta plus cosine squared phi sine squared phi, which after 2 or 3 simplifications you factor and use the trig identity sine squared plus cosine squared is 1 several times. This will come out to just sine of phi. Actually, it comes out to square root of sine squared of phi, which is equal to sine phi, and phi is between 0 and pi. Okay. So now that we have all that, we can actually compute the integral now. First, I should have put the bounds on this parameterization. Since it's the top half of the sphere, theta goes all the way around, but phi only goes halfway, so it goes to pi over 2. Okay. So the original integral, what we do is the bounds of the integral become the bounds of our parameterization. So 0 to 2 pi, 0 to pi over 2. And we substitute for z and x the coordinates of the parametrization. So here is the x component of the parametrization. We will substitute that in for x. Here is the z component of the parametrization. We'll substitute that in for z. And we don't see any y's in our function, so we don't have to worry about substituting that. So z is cosine phi, and x squared is sine squared phi cosine squared of theta. And the order that we wrote the integrals, this needs to be d theta d phi. Or we could do it in the other order and just swap the two integrals. Either way is fine. Okay, to integrate cosine squared, we use the trig identity. Cosine squared is equal to 1/2 1 plus cosine of 2 theta. And so, integral of 1 from 0 to 2 pi is just 2 pi. And the integral of cosine 2 theta is 1/2 sine of 2 theta. And if we evaluate that from 0 to 2 pi, that's just 0. We just get 0 minus 0. So really, the first integral in the variable theta just gives us a factor of 2 pi, which cancels with the 1/2 we have, so we just get a pi out front. And now we're integrating sine squared of phi times cosine of phi. And here we can do a nice little substitution. U is sine phi, and du is cosine phi d phi. So this just becomes the integral of u squared. And let's see, the new bounds. When phi is 0, u is sine of 0, which is 0. And when phi is pi over 2, u is sine of pi over 2, which is 1. And so the integral of u squared from 0 to 1 is 1/3, giving us our final answer of pi over 3.